Hi everyone, I'm Shensen from Northeastern University. In recent years, with the increasing popularity of mobile computing and Edge AI, mobile platforms have become an important carrier of DNA applications. Multi-person pose estimation is one of the popular DNA applications that play an important role in many fields, including autonomous driving, abnormal behavior detection, and behavior recognition, and has made impressive progress with joint efforts. The multi-person pose estimation can be achieved mainly in two design methodologies, which are the top-down method and the bottom-up method. The top-down method performs pose estimation on a single person who is captured by a detector in advance. The accuracy will be dependent on detector, which might fail to find all persons when they are close together. And the overall inference time will increase with the increasing number of people in an image frame, which is not efficient for multi-person pose estimation. On the other hand, the bottom-up method predicts the human key points for all people in an image. At the same time, the bottom-up method usually has smaller model size and fewer computation counts, making the bottom-up methods more desirable for fast multi-person pose estimation. To achieve high accuracy, state-of-the-art methods usually tend to have a large model size and complex post-processing algorithm, which causes intense computation and a long end-to-end latency. It also means that they are unfriendly to the mobile devices. But in application, we need a more lightweight model which can realize high-speed inference. To solve this problem, we want to build a post-estimation model with good accuracy on mobile that has small model size and simple post-processing algorithm. We build a new architecture optimization and import the weight pruning framework to get a smaller model, and we use hardware-friendly operators to achieve fast inference on mobile devices. We also choose the bottom-up method to decrease the time cost by post-processing. In this work, we built a new weight pruning framework for the post-estimation model. The DNN weight pruning mainly consists of the following three schemes. The first is the unstructured pruning that prunes weights at an arbitrary location. This pruning method is flexible to the model. Although the unstructured pruning can achieve high compression rate, this kind of pruning might irregular the original model shape. The second one is the structured pruning that prunes whole filters or channels for convolution layers. This kind of method can get good accuracy and achieve the acceleration on hardware devices. The third one is fine-grained structured pruning schemes that combine the high accuracy and high hardware parallelism, but it needs compiler support in application. Besides the DNN model inference, the data post-processing is another essential part of the post-estimation process, which calculates and groups the key points of each individual person obtained from DNN inference results. Different post-processing algorithms will significantly affect the end-to-end running time for post-estimation. Thus, choosing appropriate post-processing algorithm is also critical for both speed and accuracy consideration. As for our contribution, the first one is that we propose optimization framework here. We optimize the model architecture and use the weight pruning to get smaller model according to our sensitivity analysis of different layers. And we facilitate fast and accurate post-estimation model on mobile. The second one is mobile-aware architecture optimization. We choose the desirable depth for model and replace the model unfriendly operators to realize high-speed inference and good accuracy on mobile devices. We also choose a post-processing algorithm that can achieve high speed after the model inference. The last one is that our model can achieve fast inference and maintain relatively good accuracy on mobile devices, which enable post-estimation application on mobile devices, and our work can raise the promising future of the fast post-estimation on mobile. For the backbone depth, we do some experiments and find the deeper backbone provides better accuracy, but higher latency as the table here. We just select the durable depth for backbone to get better results both on accuracy and latency. As for the refinement blocks that are used in the model to get higher accuracy, the first two refinement blocks improve accuracy most significantly, and the latter refinement blocks only provide minor improvements. And in application, considering the latency, we just use one refinement block to improve the accuracy. In order to implement the post-estimation application on mobile devices, some mobile-aware architecture optimizers are needed here. The 7x7 convolution layer is inefficient for inference on mobile devices, so we replace it with 3 consecutive 3x3 convolution layers so that the receptive field is remained, but the inference speed is much higher. As for the post-processing, we compared different post-processing methods on desktop CPU and find that the PF method performs better than others. For the weight pruning framework, we adopt suited pruning strategy in our work. Because the sparse computation introduces execution overhead, we only prune some layers with a ratio that exceeds a threshold that can achieve the acceleration. So, we either prune with a high ratio on some layer or not prune. As for the sensitivity analysis of the model, we find the backbone of model has a higher tolerance for pruning, and in the refinement block, the PF branch is more sensitive than the heatmap branch. So we apply high ratio on backbone and heatmap branch, but less aggressive ratio on PF branch. As for the results, compared to the state-of-the-art post-estimation methods, our work has relatively high accuracy and a smaller model size, and the post-processing of our work is friendly to the mobile devices. The accuracy of our model is higher than the lightweight open pose, and the number of parameters and computation flops are all less than other state-of-the-art works. As for those state-of-the-art works, although they have higher accuracy, they either have large model size or unfriendly post-processing algorithms, which means that they are hard for us to implement them on mobile devices. After we replace the mobile unfriendly operators, we test the inference latency on Samsung Galaxy S10. We achieve more than 3 times speed up than the lightweight open pose and get higher accuracy. Here is a demo video. We run our application of post-estimation on the Samsung Galaxy S10, and the model used in the demo only has one refinement block, and the backbone of it is revised ResNet 50. The model we used has average precision at 41.5 and only have 3.15 million parameters. The computation of our model is only 8.3 G-flops, and the FPS of our application in demo video is 6. The first video will show our mobile applications for post-estimation, and we can find that we get good results with relatively small number of people. The arms and legs can be totally marked, and even there are only half of our arms or legs in the visual field, they can also be found by our application. And when the human bodies are overlapped, our application still can find the bodies of each person and mark them correctly. The second video shows that our model still can get good results for the multi-person situation. In the multi-person situation, our application still performs good when there are many overlapped bodies. The arms and legs can be connected correctly for each person.